Okay, this is 215, Sears book, University Physics. So we have a turtle crawling on a straight line. Again, that makes it one-dimensional, which we'll call the x-axis with the positive x direction to the right. The equation of the turtle's position as a function of time is. So the position as a function of time is 50 centimeters plus 2.00 centimeters per second times t minus 0.0625 centimeters per second squared times t squared. So it's kind of a parabola, t squared t. So when t equals 0, the displacement is 50 centimeters. So he starts out at 50 centimeters. It says find the turtle's initial velocity, position, and initial acceleration. So let's just look at the rest of the problem. See at what time t is the velocity of the turtle? 0. How long after starting does it take the turtle to return to its starting point? At what times t is the turtle distance 10 centimeters from its starting point? What is the velocity? All kinds of questions. So it all comes down to taking the derivatives to find the other two terms. So we know the velocity as a function of time is equal to the derivative with respect to time of the displacement. And it's pretty easy because it's a polynomial. So this derivative of a constant is 0. The derivative of t is 1. So we get 2 centimeters per second. T goes to 1. You see the units work out, get centimeters per second. And then we subtract 0.0625 times the derivative of t squared, which is 2t. And we have units of centimeters per second squared. So we can clean that up a little bit. 2 centimeters per second minus 2 times 0.0625. 0.0625 times 2 is 0.125. 0.125. I'm going to go ahead and put the units with the constant times t. Okay, so that's the velocity. So you can see when t equals 0, we have an initial velocity of 2 centimeters per second. It means it's moving from left to right, positive velocity. And then the acceleration as a function of time is the derivative with respect to time of the velocity. So we go to this previous equation here and take the derivative of that. Well, the derivative of a constant is 0. The derivative of t is 1. So the acceleration is negative 0.125 centimeters per second squared. So the acceleration is constant because there's no t involved. So to answer the first question, part A, what are the initial velocities? Well, initial means t equals 0 seconds. So if we plug t equals 0 seconds into the displacement, we'll get 50 centimeters. If we plug 0 into the velocity, we get 2.00 centimeters per second. And the acceleration at time t equals 0 is the acceleration at any time. So we get that. And what this means, the negative acceleration means that the velocity is getting smaller until it gets to 0, and then it'll come back. So what's going to happen here is the thing's going to start moving from right to left, from left to right, because it's a positive velocity, and it's going to be moving at a velocity, and it's going to slow down until it stops, and then it's going to go back the other direction. So there's some maximum displacement from the initial point. There's also a point in time where you're going to come back to the initial displacement, which is 50. Okay, so now that we know that, it says at what time t is the velocity of the turtle 0. So all you have to do is use this relationship here and set the velocity equals 0 and solve for t. So we're going to take this velocity, we're going to say that's 0 meters per second is equal to 2.00 centimeters per second minus 0.125 centimeters per second squared times t, solve for t. So you'll subtract this from both sides, and I'm going to put this onto the left-hand side. Actually, why don't we move this to the left-hand side, make it positive. So if I take the term that involves t, and then move that to the left-hand side, it becomes positive. Then I have the other term stays there, and then you solve for t by dividing. And you see the units, centimeters, cancel out. Take the reciprocal of the denominator, you'll get seconds squared over centimeters. Centimeters cancel out, you only have seconds left. And so we get 2 divided by 0.125. And the units are, the time is 1600. That's wrong. What do they do? Oh, it's 200. 2 divided by 0.125. You get 16 seconds. And we have 3 significant figures, so put there 16 seconds. Okay, I'm just checking my answers. I do have answers for odd problems. Okay, then the next question. How long after starting does it take the turtle to return to its starting point? So the starting point is 50. So what we do is we make the displacement 50 centimeters. So what I'm doing is I'm going back to this equation here. I'm going to put 50 centimeters in here. There'll be 50 centimeters on the right-hand side. So let me just copy this. I'm just going to drag it over here because I have the hardest time with, whoops. Okay, so I'm going to just take this, move it down. So there's my displacement. So what I'm going to do is put the displacement 50 centimeters, and then I have the equation on the right-hand side. Okay, so you see these are going to cancel out. And then I'll move this to the left-hand side to make it positive. So I'll get positive 0.0625 centimeters per second squared. Actually, we're going to move both of them to the left-hand side because we're going to have to factor out something here. So we'll get, this will be positive. This becomes positive by moving to the left side. This becomes negative. So I get negative 2.00 centimeters per second times t equals 0. You factor out the t, so you get t times 0.0625 centimeters second squared times t minus 2.00 centimeters per second equals 0. So when I factor a 2 out of here, I get just t. factor t out of here, he gets its constant. So there's two solutions. One is t equals 0. So for this product to be 0, this t is 0, which just tells us that one of the times that you're at 50 centimeters is the initial time. And then you solve, so the other one is that the term in the parentheses is 0. So we have to figure out what time that happens. So that also is in the solution. So if we solve for that, what we'll end up with is 2 centimeters per second. That's what I'm doing. I'm moving this to the right-hand side and then dividing by the coefficient in front of t. And again, you see the units work out because what we have is centimeters per second, and I multiply by the reciprocal. So these cancel out. That cancels out. You get seconds. And it should be more than the time it, if we go back and look at this, it took 16 seconds to get to this point. So it should take more time than 16 seconds to go here and back. But it shouldn't be twice because, maybe it does. Actually, I think it is just twice, just for symmetry. We'll see what happens. So you take 20, or 2, I keep wanting to divide by 20. 2 divided by 0.0625, and you get 32 seconds, which actually, I just said it was going to be twice that. Okay, so it's 32 seconds. And that's because of symmetry. You're going to start out here. The acceleration is constant, so you slow down here to 0, and then you speed up, and the the initial velocity going this way ends up being the same as this rebound velocity, except it's going the opposite direction. We'll see more about that later. Okay, what else we got next? At what time is t is the turtle distance 10 centimeters from its starting point? What is the velocity, magnitude, and direction of the turtle at each of those times? Okay. So we haven't actually figured out the distance it took to stop. I think we did, or did we? Found the time it took to stop somewhere here. Yeah, but we never calculated the distance. So you take this time and you plug it back into the displacement equation and find out the distance after a certain amount of time. So let me copy this equation again. So actually it says what distance, what times, and then ask the velocities. Okay, so we're going to have to solve for the time, and then once we have the time, we use that time in the velocity equation to calculate the velocity. So, so this is 50 centimeters. So if we go another 10 centimeters, the part for part D. So this is part D. What we want to do is figure out what time it takes to go another 10 centimeters from its initial starting point. So I put 60 in there because the initial point is 50. So the issue here is that you're going to have to solve a quadratic equation. So let's move everything to the left-hand side. So this will become positive, this will become negative, and then we'll combine those two. So you'll have negative 0.0625. Oh, it's positive. I said it was going to be positive. I didn't change it. 0.0625 centimeters per second squared times t squared minus 2.00 centimeters per second times t. And if we have 60 and we subtract 50, we're going to have 10. So it's going to be plus 10 centimeters equals 0. Now, how are we going to solve this? Well, one way would be to use the quadratic formula. Probably the best thing to do is to get these all to be integers. Because the solution doesn't matter if you multiply this by a constant factor, constant number, it's not going to change it. So if you take the reciprocal of 0.0625, you get 16. So I want to multiply each term by 16. And what that'll leave me with is t squared, and I have to have the units here. So it's 1 centimeter per second squared. Okay. Then 2 times 16 is 32, so I have 32 centimeters per second times t, and plus, I multiplied that by 16, I get 160 centimeters equals 0. Okay, so now the question is, how do I factor that? Now, I don't know if you can actually do it. And you're going to get two solutions. You're going to get two positive solutions because it's going to move from left to right. It's going to go through that position, and it's going to go to its maximum extent, and it's going to come back. So we're going to have two solutions. They should be both positive. And so how would we do this if we tried to just factor it? Well, you have to think of two numbers multiplied together to give you 160, which is going to be, 16 times 10. If you add those together, you get 26. So that's not going to work. What else do we have? They maybe just have to use the quadratic. Let me just look at the answer just to see. Yeah, it's not easy. So we're just going to have to use the quadratic formula. So what we get is, A is 1, B is negative 32, and C is 160. And I'm going to leave the units off because we're just solving the equation here. So you get minus B plus or minus square root of B squared minus 4AC all divided by 2A. So 32 squared minus 4 times 160 is 384. So negative times a negative is positive. 32 plus or minus the square root of 384, all divided by 2. And the square root of 384 is 19.6. So we get 32 plus or minus 19.6 divided by 2. And that's going to give us two solutions. So that's 32 plus 19.6, whole thing divided by 2, and I get 25. So one solution is 25.8 seconds. That's for the plus. And if I subtract 32 minus 19.6 divided by 2, I get 6.2 seconds. Okay, so those are the two times, which are the right answers. Then it asks for what is the velocity, magnitude, and direction of the turtle at each of these two times. So now we take that time and we go to the velocity equation. So I'm going to copy that down from previous. It's right here. For some reason, I don't think it doesn't like to copy when I'm in a two-screen mode here. Actually, that didn't work either. Why doesn't that copy? Okay. Don't know why. So that's why I ended up having to clone this thing. So I can just drag it. Unfortunately, I have to drag it across multiple pages. Probably easier just to write it down. One more. So you should get a positive velocity at the lower time and a negative velocity at the higher time. So this is v of t. So what we want is v of 6.2. So we get 2.00 centimeters per second minus 0.125 centimeters per second squared times 6.20 seconds. And so we get 2 minus 0.125 times 6.2 is 1.23. 1.23 centimeters per second, which is positive, which is what we expected, and then you can do velocity at 25.8 seconds, 2.00 centimeters per second minus 0.125 centimeters per second squared times 25.8 seconds. So you get 2 minus 0.125, oops, try that again, 2 minus 0.125 times 25.8, and you get negative 1.23 in centimeters per second. So again, because symmetry and its constant acceleration, you get velocity as it goes out is positive 1.23. When it comes back is negative 1.23. Now, what is the velocity of the turtle? Okay, we got that one. And okay, now the question is, they have a third number, and what that would be is a distance of negative 10. So depending on how they define distance, and so since they've got a third answer, we also need to look at the case where this is 40 instead of am I doing this right here? This is 40 instead of 60 because it's 10 centimeters on the other side. So that'll give us our third solution. That's what they're looking for. I was wondering how they were going to define that. So we're going to do this whole thing again. Okay, so doing the same thing we did before, you're going to move this to the right-hand side so it becomes positive. This term will become negative. And then this is 40 minus 50, so it's going to be negative 10. And that all equals 0. So we're going to multiply by 16 again. And so we'll get, I'm just going to do the equation. So you get t squared minus 32t minus 160 instead of plus 160 equals 0. So if we plug that into quadratic equation, you get negative b plus or minus the square root of b squared minus 4a, and this is where the difference comes in. You got negative, c is a negative 160, all divided by 2a. So we're going to have 32 plus or minus the square root of something. So you get 32 squared, inside, plus 4 times 160 instead of minus. And I get plus or minus the square root of 1664 all divided by 2. Square root of 1664 is 40.8. So we get 32.0 plus or minus 40.8 all divided by 2. And in this case, we only take the positive, because if we have a negative, we're going to have a negative time. And we're not interested in negative time solutions. Okay, so what do we get? 32 plus 48, or 40.8. 40.8 divided by 2, 36.4 seconds. So that is our, using the positive. So now, again, we find the velocity. We use the velocity equation, which we had somewhere here. There it is. Drag it the other way. Okay. So that is our velocity as a function of time. So we stick in our new time, 36.4 seconds. So we get 2.00 centimeters per second minus 0.125 centimeters per second squared. Whole thing times 36.4 seconds. So we get 2 minus 0.125 times 36.4, and so I get negative 2.55 centimeters per second. So that's the third solution. So let's just show what's happening here. So what happens is we're going at 2 centimeters per second to start with. We slow down until we get 10 centimeters in, which the velocity slowed down to a positive value. Then we go here to 0, then we come back. We have the same velocity but different sign, and then the third point is 10 centimeters to the left of the starting point, and it's sped up more, and that's why we have higher velocity. Okay, final thing is to draw the x versus t, v sub x versus t, and a versus t for some time, for the time interval 0 to 40 seconds. So we just need some numbers here. So at t equals 40 seconds, so we can set up our scale. So we have to actually plug that back in to the original equation. So what I'm going to do is I'm going to go back and I'm going to find the page with the velocity and stuff, and I'll copy it all the way to the end. Okay. Okay, so those are so now we just have to plug in 40 seconds. So I'm just going to do it and give you the answer and you can check it. So I'm going to take 50 plus 2 times 40 minus 0.0625 times 40 squared, and I get 30. So x equals 30 centimeters. V of 40 seconds. So I plug that into the second equation. So it's 2 minus 0.125 times 40, and I get negative 3 centimeters per second. And my acceleration is constant. It's going to be negative 0.125 centimeters per second. So that's at t equals 40, t equals 0, x of 0 equals 50 centimeters. V of 0 is 2 centimeters per second, and d the acceleration at 0 is negative 0.125 centimeters per second. The only thing I really need now is I need just the time where this goes to 0 velocity, and also the corresponding displacement at that point, which I think I did already. So isn't that what they asked somewhere here? At what time does the turtle's velocity 0? Okay, so that was equal to 16 seconds. Okay, so at t equals 16 seconds, v equals 0 centimeters per second, and x equals x max, whatever that was. Did we ever calculate that? I don't think we did. So we could go to the extra trouble of finding what that maximum displacement is. All we have to do is plug, to find this, we just have to plug 16 into this equation. So let's go ahead and do it. So we're going to take 50 plus 2 times 16 minus 0.0625 times 16 squared. So I get 66. So that's the maximum displacement. Okay, with all that, we should be in good shape. So we're going to make up 3 graphs. We'll make up one graph and then we'll clone it, just so we have all these. So this is t equals 0. We have t equals 40 out here. Let's go halfway. T equals 20. Halfway again. So that's 10. That's 30. T equals 16 is going to be somewhere about right here. 16. Okay. So I'm going to group that together. I'll just make 3 copies of it. We may actually go to negatives. So I may have to make some slight modifications, but okay, so this is x, a function of time. We're going to say this is 50, this is 100. So t equals 0, we're here. At 16, we're at 66. And at 40, we're somewhere. Okay. Velocity is a function of time. Starts out at 2 and goes to -3. So that's, I'm going to have to make some modification here. So let's group that. So what I'm going to do is I'm going to shift this thing down. To about there. So this is going to be 2, and this will be -3. And what happens with the velocity is it's linear, so it just starts up here and then goes straight. It should intersect, if I drew this correctly. So maybe move that up a little bit. Okay, so that's the velocity. Initially 2 at 16 seconds is 0, then it goes that way. The acceleration as a function of time, again, it's a negative thing. So let me ungroup this stuff and just make this direction like that. And it's -0.125. So this is acceleration as a function of time. And it's just going to be a horizontal line at negative 1.25. So that's the acceleration. This is v of t. This is a of t. This is negative 0.125. Okay, and then finally, this thing's going to be a parabola. It's going to look something like that, and then it goes down to something like that.